In this video, we're going to look at two different topics. First one is the general power rule, and then second, we will talk about the chain rule. So the general power rule, you may remember earlier in the course, we saw this formula, which we're going to call the power rule. It just tells us how to take derivatives of powers of x. So we said if we're differentiating x to the n, we get n times x to the n minus 1, and we said that was valid for any positive integer n. So what we're doing with the general power rule is we're just expanding this rule to include a few other n values. So now we're going to say this applies where n is any rational number. So when we say rational number, we're talking about all the fractions, including negative fractions. So that would include things like, say, positive 2/3, but also something like negative 4/5. It also includes all the negative numbers and 0. All the negative integers and 0, I should say. So all the fractions and all the integers are now included in this general power rule. So we're going to do some practice with this general power rule. Before we do that, we'll do a quick recap of our exponents. So essentially 3 different exponent rules that we want to be comfortable with here. If you have something like cube root of x, if we want to rewrite that in exponential notation, we're going to write that as x to the 1/3. Similarly, if you had a 4th root of x, you'd write x to the 1/4. Now, if you had a root, let's say a 7th root, and then the x is raised to a power inside that root, then we write that, for example, as x to the 8/7. So the numerator of the fraction in the exponent comes from whatever power is on the x, and the denominator of the fraction in the exponent just describes the type of root. Okay, and then third rule is, what do we do if an expression is in the denominator? So if we have something like 1/x to the 4th, when we rewrite that in exponential notation, that becomes a negative exponent. So this becomes x to the -4. And then this last item here, that's really just putting all 3 rules together. So if we have 1 the 7th root of x to the 11, well, the exponent on the x is going to be negative because we were in the denominator. It's going to be 11/7. Negative 11/7 overall for our exponent. So that's the recap of exponents that we need to now apply the general power rule. So let's go through a few quick examples of finding some derivatives. Okay, let's look at part A. So in part A, we're given the function f of x equal root x. And so you could say, well, first thing I'm going to do is just rewrite this in exponential notation. So you could say that's x to the 1/2. You don't necessarily need to do that on another line. And then we're going to take the derivative. So in the usual way with taking derivatives of powers, the power comes down in front. So we get this 1/2 here, and then the power on the x decreases. It goes down by 1. So you go 1/2 minus 1 gives you minus 1/2. And that's how we get the new exponent on the x. So then you could leave your answer like this, or you could put it back into the radical notation, where you write 1/2 root x. Okay, let's try a few more like that. So part B, our function is 1/x. So first thing you might want to do is just rewrite your function. If you want, you can do that just right beside the function itself, and then applying the power rule, our derivative f prime of x would be negative x to the -2. So remember, to get the new exponent, you're just taking your old exponent and you're subtracting 1 from it. So -1 minus 1 gives us a -2. So overall, negative x to the -2, and then you could rewrite that as minus 1 over x squared, because the negative exponent is just going to send this x squared down into the denominator. So 2 good ways of giving your answer. For part C, okay, we've got 5 times the 4th root of x cubed. So again, let's do this trick of rewriting our function here. So that's 5 times x to the 3/4 if we want to write that in exponential notation. And then let's apply our power rule. So to get our derivative, remember this exponent is going to come down in front, it's going to multiply with any coefficient that's sitting there. So when we multiply the 5 times the 3/4, we get 15/4, and then the exponent decreases. So we go 3/4 minus 1 gives us minus 1/4, and that's going to be our new exponent. So 15/4 times x to the minus 1/4. And then if you like, you could rewrite this in different notation. You could say that negative exponent is going to send the x to the 1/4 down into the denominator. And if you want, you could also express that x to the 1/4 as the 4th root of x. So I'll just rewrite this so that you can see it a little bit more clearly. You would have the 15 on top. On the bottom, you'd have the 4, and then that 4 would be multiplied by the 4th root of x. So often if you have a coefficient times a root like this, you'll put a dot in the middle just so that it's more clear that this 4 is a number, and then the second 4 is describing the type of root. It's just a little cleaner to read. So that's why we write it like that. Okay, so again, you can give your answer in either format here, just whatever you're comfortable with. And last part of practicing these general power rule examples. So we've got 12 over root x cubed. So let's rewrite that. I would say that's 12 x to the, well, it's going to be minus, because we've got this expression in the denominator, minus 3/2. Okay, so there's our function there, and then let's do our power rule to get the derivative. So f prime of x, well, the minus 3/2 is going to come down and multiply with the 12. So that's going to give us minus 18. And then the power is going to decrease. So if you've got a negative exponent, it's going to become more negative when you take the derivative, because you're going minus 3/2 minus 1. Overall, that's going to give us minus 5/2. Okay, so that's going to be our new exponent. So there's our derivative, minus 18x to the minus 5/2. So we've now had a little bit more practice with the power rule, and we also practiced our exponent rules along the way. So you can see why we first introduced this power rule just with nice positive integers. Took some time for that to sink in, and then now we've practiced the exponent rule so that we can do more general derivatives. So that's it for the general power rule. Now we're going to get on to our second topic, which is the chain rule. So imagine we have a situation where we've got a function inside another function. So we'll see an example in a minute. So f is being applied to something like g of x, and we want to take the derivative of that. So the derivative of f of g of x is going to work like this. It's going to have two parts to it, two quantities that are being multiplied together. So first thing we're going to write down is f prime of g of x. And if you describe that to yourself in words, you would say that's the derivative of the outside function, f being the outside function. So it's the derivative of the outside function keeping the inside function the same. So the g of x is staying the same, but we're taking the derivative of the outside function. And then we multiply by g prime of x. So in words, you would say that's the derivative of the inside function. Okay, well, let's do an example. I will put a box around this just so that it's easy to find if we need to look back on it. Put a star beside it because that's going to be quite an important rule. And let's try an example of this chain rule. Okay, so we'll do some bigger examples in a moment, but for now I just want to illustrate some quick examples. All right, so let's say our function y looks like x to the 7 plus 3x all cubed. Okay, so the idea is we've got this inside function, x to the 7 plus 3x, that's what's acting as our function g. And then the function f is the function that cubes things. Okay, so think of f as looking like this. And what we've got is f of g, because we're taking the function g and what are we doing? We're applying f to it, we're cubing it. Okay, so let's see if we can follow along with the chain rule. So what we're supposed to do to get our derivative y prime So we're supposed to keep our inside function the same. We're keeping that x to the 7 plus 3x on there. And we're taking the derivative of the outside function, which is the function that cubes things. So essentially that means just deal with this power 3 here. Let's deal with that in the usual way. So we bring the 3 down in front, keep the inside function the same, and then decrease the power to 2. So that's what we mean when we say f prime of g of x. Deal with the outside part, which is usually the power, and keep the inside function the same. Okay, then we multiply by the derivative of the inside function. So this part here, this is going to be our g prime, or derivative of the inside function. So if this stuff here was g, then g prime is going to be 7x to the 6 plus 3. So there we go. We took the derivative of the outside function, kept the inside the same, and then multiplied by the derivative of the inside function. So that's usually the most intuitive way of thinking about the chain rule. There is sort of a cleaner version in terms of how to write it down. So I'm going to show you the alternative version, and we'll just work through exactly how it's the same as the first version. So here's our second version of the chain rule. So if we read this, it says dy by dx equals dy by du times du by dx. So on an intuitive level, this seems like it should be true. Just kind of notationally, it looks like it should be true because you could sort of imagine the du's canceling over on the right side here. So it seems true that, yeah, both sides should equal dy by dx. But let's think conceptually about what this is saying. This is saying if you take the derivative of a function y, or if you want to take the derivative of a function y with respect to x, you can break it down into steps. You can say take the derivative of y with respect to u first, and then multiply by the derivative of u with respect to x. So let's see an example and understand how that really is saying exactly the same thing as we said above. So let's take that same function y that we were working with earlier. So y is equal to x to the 7 plus 3x all cubed. So the trick for using the alternative version of the chain rule is just to give a new name to the function that's acting as your inside function. So you could call that g, but in this version of the chain rule, we call it u. Okay, so we say we can rewrite y as u cubed. That's just saying y is the inside function cubed. And then we record for later what that inside function actually is. So u is x to the 7 plus 3x. Okay, then we break out our chain rule. So here's our alternative version of our chain rule, which says dy by dx equals dy by du times du by dx. And we just look up at our functions here. So we said y is u cubed, therefore dy by du is equal to 3u squared. Okay, and then continuing with our chain rule, we're supposed to multiply this by du by dx. Well, we said u was x to the 7 plus 3x. So taking the derivative of that, we get 7x to the 6 plus 3. So at this point, it looks a little different than our previous answer, but remember what u was. U was x to the 7 plus 3x. So if we put everything back in the language of x now, we get 3 times x to the 7 plus 3x all squared times 7x to the 6 plus 3. So that is the same answer that we had up at the top of the screen from the first version of the chain rule. So here are the takeaways that I really want us to think about after having had this discussion. So first takeaway is that there are 2 versions of the chain rule. That's the first thing to remember. Just 2 ways of writing the same thing. This second version, the alternative version, we're going to use that later in the course. So let's just store that away that, okay, there is this alternative version of the chain rule. We're going to talk about it later in the course. But for right now, for doing our calculations, most people find the first version to be the more intuitive version. So that's what I'm going to stick with when we're going through our bigger examples. I'm going to stick with this, I call it the intuitive version of the chain rule. So with that, we're ready to jump into a whole bunch of examples. We will practice the chain rule until we're really comfortable with it. So we're going to start over here, and we're going to do all of our examples now on a new page so that we can see everything developing. So the problem is to find dy by dx, and in this example we're just going to do 4 relatively short parts here. So for part A, y is equal to 2 times 1 minus 5x to the 4th raised to the 7th power. Okay, so dy by dx, this represents our derivative. So we're going to apply the chain rule here. The outside function, if we want to just sort of imagine a picture here, the outside function has 2 times something raised to the 7th power. So if we were going to take the derivative of something like that, the 7 would come down in front, multiply with the 2, so we'd have 14, and the power on the bracket would decrease to 6. Okay, so we're going to keep the inside function the same throughout that process, and then multiply by the derivative of this inside function, which would be minus 20x cubed. So that's great. The only cleanup you might do here is you might multiply the 14 with the minus 20x cubed to get minus 280x cubed times the 6th power of 1 minus 5x to the 4th. Let's say our function y is 10x cubed minus 6 times 1 plus 5x to the 4th. So taking our dy by dx, our first term does not involve a chain rule. We just take the derivative in the usual way. So it's 30x squared. And then we get into this expression here, which is going to require a chain rule. So we're going to take the derivative of the outside function first. That's going to give us minus 24 blah cubed, where blah just represents leaving our inside function the same. So you get minus 24, 1 plus 5x, all cubed, times the derivative of the inside function, which is 5. If we like, you could say that's 30x squared minus 120. 1 plus 5x, all cubed. Normally we collect all the coefficients at the front just to make it easier to read. Try another one. Let's say y is the square root of 2 plus 4x cubed. Okay, so if you like, when you first approach this problem here, you could say, oh, I'm going to rewrite this in exponent notation. You can say that's 2 plus 4x cubed to the 1/2. Just to make life easier if you want. Then you can say, well, to get dy by dx, I'm going to deal with the outside function, which is the function that raises things to the power 1/2. So we're going to get 1/2 times the inside function now raised to the power minus 1/2. So that's just us applying that power rule. We're going to keep the inside function the same, and then multiply by the derivative of the inside function, which would be 12x squared. And then if you like, you could do a little bit of cleaning up here. So you could multiply the 1/2 and the 12x squared to get 6x squared. And then if you like, you could take this expression that's raised to the minus 1/2, and you could say that gets sent down into the denominator. You could even write it in the radical notation if you like. So like that would be one way of writing it, or another way of writing it, you could just leave it in the exponential notation, say 6x squared times 2 plus 4x cubed to the minus 1/2. So generally, I just give a couple of different ways of writing it because, you know, if you're doing some homework, you're checking your answer in the course pack, you just want to be comfortable with the fact that your answer could be expressed in a couple of different ways and still be correct. Okay, let's say our function y is 1 over 1 plus 17x squared raised to the power 4. So first thing I might do here is just rewrite the function. I could say, oh, well, that might be nicer if we wrote it as 1 plus 17x squared to the power minus 4. And then we'd say, well, let's do our chain rule. So we're going to deal with the power -4 first. So -4 comes down in front. The exponent becomes more negative. So if you go -4 minus 1, you now have -5 in your exponent. keep the inside function the same, and then multiply by the derivative of the inside function, which would be 34x. Multiply the negative 4 and the 34, so minus 136 x is what you get there, and then that's times 1 plus 17x squared minus 5. And then if you want an alternative way of writing that, minus 136x over, well, you could say that's over the 5th power of 1 plus 17x squared. So just two different ways to write it. And again, just emphasizing the exponent rules. That's why I'm always saying there's a couple of different ways to write it, just so we can practice all those exponent rules as we go through this process. So that's our first worked out example of using the chain rule. We're going to do quite a few more examples just to really get comfortable with all the varieties of the problem that can come up. So we are going to simplify y prime, where y equals 4x squared times 8x plus 7 raised to the 6th power. Okay, some of our upcoming examples are going to be multi-concept examples, so that's just something to watch out for. This function y here is actually a product. So we can think of this as being our u, and that stuff there as being our v. So maybe let's just have a quick refresher here of our product rule. If you're trying to take the derivative of something that looks like uv, our product rule says go uv prime plus v u prime. So let's try that. Okay, so here's our y prime. We're going to take our first factor, which is 4x squared, and we're going to multiply that by the derivative of the second factor. Okay, now because we've still got more work to go on this line, I'm not actually going to take the derivative of that second factor. I'm just going to write literally take the derivative of 8x plus 7 to the 6th, and we'll figure out what that derivative is in the next step. Otherwise, I would worry about maybe forgetting the rest of the product rule. Okay, and then we're going to go plus our second factor times the derivative of our first factor. Okay, well, derivative of u with respect to x is easy enough to take, so it's best just to write that down and say that's 8x. But what we really need to work on in our next step is taking this derivative. Okay, so then looking ahead, thinking about how to take that derivative, we'll notice that we've got this inside function, 8x plus 7, and then something else is happening to that. That's being raised to the 6th power. So we're going to need the chain rule to calculate that part of the expression. Okay, so y prime is equal to 4x squared times, in the square brackets, we're going to do the chain rule. So 6 will come down in front, inside function will stay the same, power will decrease, and then we multiply by the derivative of the inside function, which is 8. Okay, and then we've still got the rest of that expression there, 8x plus 7 to the 6th power times 8x. So notice that the question said to simplify our answer. And so what that means in this context, it means to factor if possible, because we've ended up with this y prime that looks quite complicated. It's got two different terms and there's a whole bunch of stuff going on. So what we'll see is that if we can do a little bit of factoring, this can be a lot easier to read and to work with. So let's look at our two terms and figure out what our common factors could be. So we could certainly take an 8x plus 7 to the 5th power out of both of these terms. We could take an 8 out of both of these terms, and we could take an x out of both of these terms. That's all that we can take out. So let's try that. Let's take all the stuff out. We're going to do 8x times 8x plus 7 to the 5th. Give ourselves big square brackets here, and we'll just figure out from both of our terms what exactly we can take out. So it'll just show us pulling stuff out here. So we're going to take the 8 out, we're going to take an x out. So after we've taken the x out, that will leave us with just a 4x here. And we're going to take the whole 8x plus 7 to the 5th out. Okay, so what's left behind from the first term then? 24x. Okay, from the second term, we're taking the whole 8x out. We're taking 8x plus 7 to the 5th out. So that's going to leave us with just a single power of 8x plus 7. So we're getting that whole 8x plus 7 here. And then in these square brackets, we could just collect like terms to clean up our answer. So I might do that in the next step just to avoid doing too much here. So then collecting all the stuff in the square brackets, you could call that, you could say all of this stuff here is 32x plus 7. Y prime would look like 8x times, we'd probably put the 32x plus 7 towards the front, and then we'd say 8x plus 7 to the 5th. So generally when you write down answers like this is just a stylistic point. You put the simplest kind of factors at the front, and then you write with increasing complexity towards the right side. It's not like you have to do that. It's just that when you're checking your answer in the course pack, you know, that's probably how they're going to tend to write their answer. So it's just for the point of view of comparing your work with someone else's work to see if they're the same. So we are going to find f prime of 1 for the following function f. Okay, so there's going to be a chain rule involved because we've got an inside and an outside function. That raising something to the 4th is our outside function. And there will also be a product rule at some point in the problem. So a common question people would ask themselves is just, oh, which rule am I supposed to apply first? Well, we have to decide, you know, is this really written as a product like that? And then you would do the product rule first. Or is it more written as a chain rule where you've got some stuff raised to a power? And I would say it's actually this situation here. So we're going to apply the chain rule first, and then we'll use the product rule a little bit later in the problem. So our derivative f prime of x, well, we're going to bring the 4th power down. Power will decrease to 3. Inside function will stay the same. So we'll recopy that. And then we need to multiply by the derivative of the inside function. So multiply by the derivative of 3x plus 2 times 9x squared plus 1. So you could actually work that out right here, but I just tend to try to not do too much in one step. So first part here was just taking the derivative of the outside function, keeping the inside the same. And then we're going to put square brackets here, and this is where we'll take the derivative of this inside function. Okay, so maybe I'll write the product rule over on the side just so we've got something to look at. Derivative of u times v is uv prime plus vu prime. Okay, so that's the pattern we're going to follow here to figure out the derivative of the inside function. So keep the 3x plus 2 on there. Derivative of 9x squared plus 1 is 18x. And then we go plus and do this the other way around. 9x squared plus 1 times derivative of the first factor, which is 3. Great. Okay, now this is where it's important to read the problem. See, this one does not say simplify. It says find f prime of 1. So that's good news. We're just doing a numerical example here. So we're going to have 4 times something cubed. So let's plug in 1 and figure out what our something would be. Well, plugging in 1, we'd have 5 times 10. Okay, so I might just call that 50. Make life easier when we get to putting this into our calculator. So 4 times 50 cubed, and then square brackets. Continuing to plug in 1, we'd have 5 times 18 plus 10 times 3. Okay, and again, if you want to make life easier for yourself before doing the full calculation, you could do just this part on your calculator. You could say, oh, that's 120. And then see, now you're typing in something relatively easy to your calculator. 4 times 50 cubed times 120. So that works out to 6 times 10 to the 7. So our function y looks like x over root 1 minus 3x, and we are going to find y prime and simplify. All right, so in looking at this structure of this function y, I would say y looks like something, not 0, just something, over something. And so that's the setup for the quotient rule. If we wanted to kind of write that more rigorously, we could say y looks like u over v. So let's remember our quotient rule. Quotient rule says if you're trying to take the derivative of something that looks like u over v, remember we start with the denominator. So we go v u prime, and the quotient rule has a subtraction in it. So it's v u prime minus u v prime over v squared. So we're going to try to mimic that as we go through this calculation. Okay, so we're going to say y prime is, let's grab our denominator, multiply by the derivative of the numerator. Okay, well, derivative of x is just 1. And then we go minus. Okay, now we're taking our numerator and multiplying by the derivative of the denominator. Okay, so for now, I'm just going to say d by dx of 1 minus 3x, all square rooted. Okay, so continuing with our quotient rule, what are we supposed to do? We're supposed to square the denominator. Okay, so let's take one more step just to get everything differentiated. So we'd have root 1 minus 3x minus x times, okay, this is where we need our chain rule. So if you want to make life a little bit easier for yourself, you could say, instead of saying d by dx of the square root, you could actually say d by dx of 1 minus 3x to the half. Okay, so doing that just, frees up a little bit of mental space when you're trying to take the chain rule. So chain rule, we want to deal with this half. We're going to bring the half down in front, and the power will decrease to the minus 1/2. The inside function will stay the same, and then we need to multiply by the derivative of the inside function. So we get that minus 3 there. And then continuing with our quotient rule, well, in the denominator, something nice is happening. We're squaring a square root. So the square root and the square will cancel just to give us a full 1 minus 3x. All right, so at this point, the question has asked us to simplify. Remember, it says find y prime and simplify. So let's talk about what it means to simplify. We want to clear any fractions and negative exponents. So let's talk about what we mean by that. So a couple of things that don't look so great here are the idea of having a half in the numerator. See, that's not nice because it's a double division. You don't want to say half and then divided by something else. If we were doing a follow-up calculation, this would be messy to work with. So we want to find a way of getting rid of that fraction. And another thing that's sort of messy is having this expression here with the negative exponent. That's messy because eventually with a little bit of algebra, we can bring that expression down into the denominator. The way that we're going to clear the fractions and negative exponents is by multiplying top and bottom by something. So let's think about what we need to multiply through by. Well, dealing with the fraction, if we want to get rid of the half, a nice trick is to multiply top and bottom by 2, because all that's going to do is just introduce a factor of 2 into the denominator, but it's nicely going to get rid of that 1/2 that we've got on top. So multiplying through by 2 will clear the fractions. And then the way you could clear the negative exponents, you can multiply by 1 minus 3x to the power 1/2, to the power positive 1/2, and whatever we do to the top, we're going to do to the bottom as well. So multiply by 1 minus 3x to the power positive 1/2. What that's going to do, that's going to multiply with this guy and just get rid of that negative exponent. Okay, the thing we need to be aware of is that we've really got 2 terms in the numerator. So it's important to have square brackets here and to understand that this 2 times the root is going to multiply with both of our terms in the numerator. If you want, you could put brackets around the denominator as well. Okay, so let's try that. We're going to take this 2 times 1 minus 3x to the half and just multiply it through. So that's going to give us 2 times the root 1 minus 3x times another root 1 minus 3x. Okay, so we could just call that whole thing 2 times 1 minus 3x for our first term. And then let's think about what's going to happen for the second term. So we're taking this 2 times 1 minus 3x to the half and multiplying it with all this stuff here. Okay, so this term is going to be minus. Well, let's think about the sign actually. We're going to have a minus from here, we're going to have an x, and we're going to have the minus 3 multiplying with that as well. So in fact, it's going to turn into a positive 3x. I think I'll just start to cross things off from this term when we dealt with them. The half is going to multiply with the 2 to cancel, and the expression to the minus 1/2 is going to multiply with the expression to the positive 1/2. That would just give us 1 minus 3x to the 0, or in other words, 1. So amazingly, when we do this second multiplication, we just get plus 3x. That's all we're getting there. And then in the bottom, multiplying this with that, you get 2 times, well, we're going to have 1 minus 3x to some power. Let's figure out what the power is going to be. So the power is 1 here. The power over on the right here is 1/2, and when you multiply things together, their powers add. So you get 1 plus 1/2, in other words, 3/2. Okay, so we're almost good here. Just need to clean up that numerator a little bit. So we got 2 times 1 minus 3x, which gives us 2 minus 6x plus 3x is what you get in the numerator. So let's call that 2 minus 3x, just to be done with it. Okay, and that's all divided by 2 times 1 minus 3x to the 3/2. So it is often true in calculus that the simplifying is harder than the actual taking of the derivatives. Simplifying is important in some problems where we're doing, let's say we were doing a follow-up application with this function, then we may need to simplify. But much of the time we will just be subbing in numerical values. So in a sense, simplifying is like a nice to have skill, but we want to focus more importantly on things like the product rule, quotient rule, and the chain rule. So here we go. F of x is root 3x squared plus 6 times 4 minus 2x, and we are going to simplify f prime of x. So we're not only going to practice our calculus rules, but we will also just do a little bit more practice with the simplifying concept that we talked about in the previous example. So I would look at this function and I would say, well, that has the pattern u times v. That's a product. So first thing we're going to do is use our product rule, which says uv prime is equal to uv prime plus v u prime. Okay, so let's start our calculation down here. Going to take our first factor, root 3x squared plus 6, multiply by the derivative of the second factor, which is negative 2. And then we go plus, and we're going to do this the other way around. So 4 minus 2x times the derivative of that first factor. Okay, so once you've written down your product rule, then if you decide, hey, I feel like doing this derivative right in that step, that's fine. So think of this as 3x squared plus 6 all raised to the power 1/2. The derivative is going to be 1/2 3x squared plus 6 now raised to the power minus 1/2 times the derivative of the inside function, which is 6x. Okay, so let's just clean this up here. So we got minus 2 times a certain square root plus, well, if you multiply the half and the 6x together, you would get 3x. So it's like 3x times 4 minus 2x times this 3x squared plus 6 to the minus 1/2. Okay, and you could even take that a bit further and you could take that root and actually put it in the denominator. Okay, so we've really got this 3x squared plus 6 all square rooted in the denominator. Okay, now the way that we're going to simplify this is we're going to need a common denominator, because the issue is that the right term here, the term on the right, is over this denominator, root 3x squared plus 6. But the term on the left is not over that denominator. So we need to make the term on the left over that same denominator in order to be able to add these terms together. Okay, so let's think about how to create a common denominator here. So if you had a number like 7 and you wanted to turn that into something over 2, you would just multiply top and bottom by 2. You'd say multiply that by 2 over 2, and that becomes 14 over 2. Right? So that idea of multiplying top and bottom by something is how you create your common denominator. So I mentioned that just so we can imagine how it works with numbers before we actually do it with roots. So if we wanted to put this over 3x squared plus 6, all square rooted, we would need to multiply top and bottom by that root. So multiply top and bottom by root 3x squared plus 6, and voila, you have your common denominator. So then you could clean up this part here and you could say, okay, well, that's just going to give us a full 3x squared plus 6. And then we've still got our second term, which looks like 3x times 4 minus 2x over that root. So see, now we're going to be able to add these two terms together. Everything is nicely over that root 3x squared plus 6. And let's just work on figuring out our numerator. So our numerator is going to look like -2 times 3x squared plus 6 plus 3x times 4 minus 2x. And I think I'll take one more step just to clean that up. So everything's over root 3x squared plus 6. If we actually did a little bit more simplifying here, you would get -12x squared plus 12x minus 12. So you could go through all the details here if you like, just to simplify that numerator. And then if you really wanted to get crazy, you could factor out like a -12 if you wanted. Call that -12 x squared minus x plus 1 all over root 3x squared plus 6. So just sort of to give you some general guidelines, for testing in calculus courses, you would certainly not have to simplify in every question, but typically you might have to simplify, say, in one test question or something like that. So it is important to have all these simplifying skills, because if we were doing some follow-up calculation, we would need our function to be simplified before we can actually use calculus for an applied purpose. So it's an important skill to have, but it's not something that we need to emphasize in every single problem. So here is our last problem for this video. We're going to say v is equal to k times the square root of L over A plus A over L. K and A here are both constants, and they're not equal to 0. L is our variable. It's a length. So specifically, the context here is that we're talking about a wave, and this v is the velocity of the wave, L is the length of the wave. And the question is, where is dv by dl equal to 0? So going into the problem, especially when it's kind of an applied problem like this, really important just to emphasize to ourselves what the constants are. So k and a are just numbers. L is our variable. Another way that we understand L is our variable is because we're seeing it in the denominator here. So it's always d function divided by d variable. So L is our variable and v is the name of our function. Okay, so let's start the process just by finding dv by dl. And then once we've found that, then we'll figure out how we set it equal to 0 and solve from there. So if you like, what I might do, I might rewrite the function v before jumping into the derivative calculation. So think of v as being k times L over A plus A over L raised to the power 1/2. Okay, and then we can find dv by dl from there. So this is a chain rule problem. The outside function is the function that raises something to the power 1/2. So that 1/2 is going to come down and multiply with the k to give us k over 2. Inside function stays the same. And then the power decreases by 1. So power becomes minus 1/2. Okay, now we need to multiply by the derivative of the inside function. So remember that L is our variable and A is just a number. Okay, so the context here is like if you were taking the derivative with respect to x of something that looks like, say, x over 7, right? We've got our variable on top and our number on the bottom. The answer would be 1 over 7. So if we're taking the derivative of L over A with respect to L, the answer would be 1 over A. Okay, and then we need to continue to take the derivative of that inside function. This A over L is a little bit maybe problematic here. You might want to write that as AL to the negative 1 because L is our variable. So then taking the derivative of that, you'd have minus AL to the negative 2. Just think of A as your coefficient and you're taking the derivative of L to the negative 1. So negative AL to the negative 2. Okay, so that was us applying our chain rule. You know, this problem is maybe slightly more complicated than the previous ones just because we've got these A's and L's floating around. So we just need to constantly remind ourselves that L is the variable and A is the constant. But we're in pretty good shape here. So let's just clean this up a little bit so that we can imagine setting this equal to 0. Remember, the question is, where is this derivative going to equal 0? So this is a situation where a little bit of simplifying can go really a long way. So let's imagine we've got this big fraction. We've got a k on top, 2 on the bottom. This expression here gives us a root in the bottom. So we've got root L over A plus, it doesn't matter how you write that, let's write that as A over L there. So all that stuff is in the bottom. And then we've got this 1 over A minus A L to the negative 2. Okay, let's call it A over L squared. Okay, so that's what we've got on top. So what we want to do now is set this equal to 0. So let's see what happens. So we've got k times 1 over A minus A over L squared on top. On the bottom, 2 times the root. And we're going to set that equal to 0. Okay, the nice thing is that whenever you have a fraction, like A over B, and that's equal to 0, that implies that our numerator is equal to 0. So if you know that your fraction is equal to 0, then you can conclude that your numerator is equal to 0. So we actually do not care about the denominator at this point. We can just say, okay, that means that k times 1 over A minus A over L squared is equal to 0. And then as a next step, we would say, oh, well, this would be nice if, we could divide through by k. Let's think about what we were told at the beginning of the problem. Well, k is a constant that's not equal to 0. So that means perfectly allowable to divide through by k. And we get 1 over A minus A over L squared equals 0. Okay, and now the context becomes clear. So what we're actually trying to do here, it wasn't totally clear at the beginning, but what we're trying to do is solve for L. So just going back to the context of the problem before we actually finish the problem, see, we had this wave and we had a formula for its velocity, and its velocity was dependent on the length of the wave, right? So the question is, where is dv by dl equal to 0? Well, the answer is going to be a certain length, a certain wavelength. So we're essentially solving for the wavelength that is going to make dv by dl equal to 0. And so we're going to say the wavelength is like 2 times A or 3 times A or 1 over A or something like that. The answer is going to depend on A. So we're going to get a wavelength described in terms of A. The way that we can see that from the algebra is you've got this equation here. It just involves A and L. L is your variable. So L is the thing that's changing and A is just some constant. Whenever you have that context, it makes sense to solve for your variable. So we're going to solve for the wavelength in terms of this constant A. So an easy way to do that, if you just have 2 terms on the left side, is to bring 1 term on either side of the equation. So you got 1 over A equals A over L squared. We can now just cross multiply here. So multiply these guys, multiply those guys, get L squared equal A squared. And then you can say, well, we can take roots of both sides as long as we realize that there's going to be a plus and minus solution. So L can be either plus or minus A. And in theory, that's the correct math. But if we think about the physics of the situation, L is a length. So let's see, we were told that in the problem. L is a length. We're given that right here. So based on our physical intuition, we should have the idea that L should be a positive number. And we actually weren't told whether A is a positive number or not. So we actually don't know whether L is equal to plus or minus A. So at this point, I might just say L should be greater than 0. If you make the assumption that A is positive, then you can say L equal A. But let's just leave it like this for now. So just as a quick summary of everything that we did in the video, we talked exponent rules. That's pretty important. So if you were not, totally fresh on that from your previous math courses, we did a bit of review at the beginning of this video just to get you up to speed. And then we talked about the chain rule. So that's really the important takeaway from the video. Our various examples combine the chain rule with the product rule and the quotient rule for good kind of multi-concept practice. And then third kind of major thing that we did was we worked on simplifying. But I would say in order of importance, quite important to understand your exponent rules and your chain rule. The simplifying, it's just something that we're going to continue to work on in every math course to make sure that your algebra skills are up to speed, because occasionally in problems you need the simplifying. You don't need it in every single problem. That's our video on the chain rule. Thanks for watching.